Good morning, guys. Today we're going to discuss the Customized Energy Output Prediction Project. This is project number 1 in the AI certification. In this project, we will build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. There's some key steps that we need to execute for this project. We're going to define the machine learning approach and output metrics. We're going to define features and algorithms. We're going to split the data and create test set to evaluate the performance, determine validation strategy, compare models, and evaluate the performance. Our problem type is, this is a supervised regression problem since the target variable is continuous. Our objective is to predict net hourly electrical output given ambient environmental conditions. Our output metric will be root mean squared error, which measures how far predictions are from the actual values in the same unit. In addition, R2 score to show variance explained. So supervised regression, metrics, RMSE. We might do MAE as well as R2. The chosen metric, RMSE, since it penalizes large errors, which is important because big prediction mistakes and power output are most costly than small ones. What are our features available? Ambient temperature, exhaust volume, ambient pressure, and relative humidity. Our target is P, which is net hourly electrical output. And then our candidate algorithms are going to be linear regression, baseline, interpretable fast, as well as random forest regression, which is non-linear and captures interactions, handles noise. So model 1 will be linear regression. It's simple, it's interpretable when we can develop our baseline. Model 2 will be random forest, which handles non-linear interactions. And the comparison will be cross-validation, RMSE. And we're going to compare linear regression for simplicity and random forest for flexibility. We're going to split our data, 80-20 split, with 74-54 rows for training, 19-14 for testing. And our validation strategy will be cross-validation, K5 on a training set. The training set, the training data will be split into 5 parts, which are called folds. The model trains on 4 folds and tests on 1 fold left out. This repeats 5 times, with each fold used once for testing, and the average performance is taken as the final score. Now we're going to switch over to our actual code to show the Python code that was developed. All right, so I am in here, I'm using IDLE. As you can see, this is the Python code that was developed to handle loading the data, splitting the data, comparing the 2 models, doing the cross-validation, and then the evaluation. And at the end of the code, it prints out the output of that code. Now I'm going to switch over into Word to show you, this is the output of the Python code. So you can see some of the output that is printed out. You can see this loading the data. It outputs the train split results. It also defines the pipelines. It fine-tunes the random forest. It evaluates the models. And the key thing that we want to look at here is the model comparison. So as you can see here, the Python code will print out the output of the model comparison. And as you also can see, the random forest tune is the better model here. Why? It's more accurate, it has a lower RMSE, and it has more explanation, which is a high R2. The linear regression is simple. and more interpretable, but it sacrifices accuracy because the data set has non-linear relationships that are captures. All right. I want to go back to just give you a summary of the final write-up based on what we've done. So the models tested were linear regression, simple, interpretable, fast baseline. The random forest will symbol of trees captures non-linear relationships. The results, the linear regression had higher errors. It was limited to straight line patterns, while the random forest had lower RMSE, higher R2, and it was better at capturing complex interactions. Our recommendation is to use the random forest for accurate prediction, but keep the linear regression as a quick interpretable baseline. Lessons learned. Always start with a simple baseline, such as the linear regression before testing more advanced models. You can learn this lower cost. Cross-functional cross-validation gives us a better sense of performance than a single trained test. Non-linear models like random test forest handles complex real-world data better. Interpreting versus accuracy is always a trade-off. And sometimes a simple model is still valuable. RMSE and R2 together give us a full picture of the model quality. Thank you guys for your time and have a great day.